So starting with the cosine angle sum. So if we have cosine, you have two angles and you add them together, be rewritten as the cosine of alpha, cosine of beta, minus the sine of alpha, sine of beta. And what I want to do is tweak this formula a little bit by saying, what happens if I let alpha equal beta? Then what I'm going to get is alpha plus alpha, or 2 alpha. So on the left, I'm going to have the cosine of 2 alpha. And on the right side, it's going to become cosine alpha times cosine alpha, which I could rewrite as cosine squared of alpha. So I'm saying they're the same angle. And then we're going to have a minus, and they're the same angle, so I can say this would be sine alpha times sine alpha, which we could call the sine squared of alpha. This is what's called the double angle formula. So if we're given the double of some angle, we can rewrite it in terms of half that angle. Now, another interesting thing about this, we know that cosine squared of alpha plus, not minus, right? The sine squared of alpha is equal to 1. That's our Pythagorean identity, right? So if you change the addition to subtraction, it doesn't simplify as much, right? It doesn't become a 1, which is pretty awesome in terms of simplification. But instead, if you subtract them, you get cosine of twice the angle you started with, which is kind of cool. It simplifies a little bit. But it turns out we can use this identity to get a couple of other versions of what we see above. So again, this is one version of the double angle formula. Cosine. There's a sine version too, we'll get to in a little bit. So what I'm going to do here is I am going to rewrite the Pythagorean as cosine squared of alpha equals, I'm going to subtract the sine squared over, so I have a 1 minus sine squared of theta. So then up above, I can replace the cosine squared with a 1 minus sine squared. So that's going to give me 1 minus sine squared of alpha in place of the cosine. And then I still have a minus sine squared of alpha. So that's going to give me 1 minus twice the sine squared of alpha. Now, there's nothing special about solving the Pythagorean identity for the cosine squared. I could have solved for the sine squared. So alternatively, in this formula, I could leave that cosine squared alone and then replace the sine squared. What could I replace sine squared with based on the Pythagorean identity?
Would it be 1 minus cosine squared?
It'd be 1 minus cosine squared, correct. Yeah, so we just flip these two. So I can replace the sine squared, and I got to use parentheses with a 1 minus cosine squared. And then we're going to have to distribute that negative. So I'll have a minus 1 and a plus cosine squared. So that means I'm going to get 2 of the cosine squareds, then a minus 1. So this is now going to be 2 cosine squared of, oops, not theta, I'm supposed to be using alphas, sorry about that. And then minus 1. So again, there's a lot of interesting relationships between trig functions. There were a ton demonstrated in section 2. There's not quite as many in section 3 here, but interesting thing that we have 3 interesting options for the cosine double angle. So I'm going to write them again, more compact. So again, cosine double angle. Oops. So cosine of twice some angle. First version is cosine squared of that angle minus sine squared of that angle. Next one, one minus twice sine squared of the angle. And the next is twice the cosine squared of the angle, then minus 1. And it turns out all 3 are useful depending on the situation we have with cosines and sines and their squares. Now, think back to algebra classes you had before. You learned about straight lines, and then we started squaring variables. And so then we had to deal with things like parabolas and relations and so on. So if we start squaring sines and cosines, that obviously is going to get way more complicated than just a single sine or a cosine. So sometimes it's nice to reduce powers of sine and cosine. So we can rewrite these 2 by solving for the squares. So what I want to do is take my cosine of 2 alpha equals twice the cosine squared of alpha minus 1, and I want to solve that for cosine squared. So I'll add the 1 to the other side. So I'm going to get cosine of 2 alpha plus 1 equals twice cosine squared of alpha. And then I can divide both sides by 2. And so what I have is that the cosine squared of alpha is equal to this fraction where we have cosine of 2 alpha plus 1 and then divided by 2. So what this allows me to do is if I have a square of a cosine hanging out in a problem somewhere and the square is making things complicated, I can rewrite where there's no square. Now, the trade-off is I have to change the period and I have a shift upward on that, but I don't have the square anymore. Now, similarly, we can solve for the sine squared in the other version. So let's do that. And I'll come back to this in a minute. So I've got cosine of 2 alpha equals 1 minus twice the sine squared of alpha. I want to solve for the sine squared, so we'll subtract 1 here. And then I'm going to have to divide by a negative 2. And to deal with the negative in the bottom, I'm just going to multiply that negative into the top. So I can multiply top and bottom by negative 1. And if I do that, that's just going to change the order of the subtraction in the top. So now I'm going to have 1 minus the cosine of 2 alpha over 2. And that's the same thing as the sine squared of alpha. So that formula right there, and then the other one with the cosine. Oops, wrong way. There we go. So my other version is the cosine squared of alpha. I'm going to rewrite it as 1 plus the cosine. Something's missing. There's my 2. Well, there should be a 2 up here, shouldn't there? So that. and written this way. So again, this is just a tweaked version of the double angle formula, but these are known as power reduction formulas. They allow us, if we have powers of sine and cosine, we can reduce the power down. One more take on these. If I do a slight tweak of the variables, and again, I've mentioned before how interrelated all these trig functions are. If you double an angle going the other way, you can cut an angle in half. So for example, if I say, let's let 2 alpha equal theta, then alpha is equal to theta over 2. Right, just reversing the multiplication, it's a division. So if we replace in the equations above the alpha and the 2 alpha with their theta versions, then what we're going to get, say for the first one, is the sine squared of theta over 2 is equal to the fraction 1 minus cosine. And instead of 2 alpha, I'm now calling that theta over 2. And I could get rid of the square by taking the square root. And then I would have to throw a plus and minus in there to compensate. This is called a half angle formula. So we can work with doubled angles and we can reverse that to work with half angles. The half angle formula is a bit more complicated because you have a fraction and you have a square root. And then you also have the plus or minus to think about. So I would say the formulas I end up using most when I'm having to clean up some more complicated trig equation that I need to solve are angle sum and difference that we looked at the other day. The double angle formula for cosine, and then the 2 other versions of that, which are the power reduction and the half angle, but they're all related to each other. Do I have them all memorized? Some days. There's a lot of identities out there. Ones that stick in my head, I mentioned before, is the angle difference for cosine. That's an important one because you can get all the other ones from it. And then from the angle sum for cosine, we get the double angle. So I mentioned the other day that I think the angle difference formula for cosine is an important one. And then my next most important after that Pythagorean, I would say would be the cosine double angle formulas, because then you can do a whole lot of stuff with them. There's a sine double angle formula too we'll look at in a sec. That's okay too, but it turns out you find you use these more than any of the other ones. All right, so I'm going to write down 2 more formulas and then we're just going to play around with them. So we have the sine half angle. For the cosine half angle, we're just going to swap variables and take the square root. So the cosine of theta over 2, based on this formula above, is going to be plus or minus the square root of the fraction 1 plus the cosine of theta over 2.
Is there no square root? Oh, I guess you already took out the square root.
Yeah, I took out the square and put the square root on the other side. So I skipped a couple steps, but based on the sine version, the cosine one has to look like that. And are those important to memorize? If you have room in your brain for them. Again, more importantly, that group is one I find most useful. All right, so one more identity, and then we'll just play around with them. The sine double angle. So I'm just going to scoot back here. So if we look at this formula here for the sine of an angle sum, sine, cosine, cosine, sine, we're going to tweak that one next. So sine of alpha plus beta is the sine of alpha cosine of beta plus the cosine of alpha sine of beta. And what I want to do is let those two angles equal each other. So alpha equals beta. So that I can just replace, say, the betas here with alphas. So I end up with the sine of alpha plus alpha, or 2 alpha, right? Double of an angle, is equal to sine of alpha cosine of alpha plus cosine of alpha sine of alpha. Now, it doesn't matter what order you multiply in. So it doesn't matter whether it's sine times cosine or cosine times sine, as long as it's the same angle. So what I have up there are twice the sine of alpha, cosine of alpha. And this is the sine double angle formula. And these formulas we're talking about are also known as identities. And they're known as identities because they're true for any angle. Doesn't matter what the angle is. They give you the same results. All right, so let's see. How about we play around now?